So I've decided that we need to split the lectures between the three-dimensional electron gas and adding interactions, just to make it a little bit more manageable. So that's why we've got a separate video here. So having dealt with the uniform electron gas in one dimension and in 3 dimensions, we're now in a position to think about adding interactions between the electrons. Of course, these interactions are going to be electrostatic, which means that we will need a neutralizing background in order to give a charge-neutral system. So we'll add a uniform positive density to our system, which will cancel out the uniform negative electron density. I should also note that it's not actually possible to find an exact solution for the uniform electron gas with interactions between the electrons, though very good approximations do exist, and we'll talk about those when we come to density functional theory. Here we're going to use, again, the Hartree-Fock approximation, which allows us to get some useful insights. So the interaction operator that we're going to be using here is the simple electrostatic case. So we've got U is a half, and remember we're using a half to avoid double counting, I not equal to j of E squared over 4 pi epsilon naught Ri minus Rj. So that's a, excuse me, that's an operator which goes over all of the electrons in the system and allows them to interact with each other electrostatically. We're going to assume a similar many-body wave function that we used before, so we're going to call it psi t. That's a trial wave function. And it's going to be made up of a combination of single particle orbitals, and then we will want to seek to minimize the energy E, which is just the standard psi t h psi t with respect to the single particle orbitals that make up our trial wave function. So I'll say WRT for with respect to the phi I of x. Notice that we can write H is equal to the kinetic energy T plus the interaction operator U. It can be shown, I'm not going to show it, but it can be shown that the ground state is found when we use the plane wave solutions that we saw for the non-interacting gas, which is a very interesting result that we'll come back to again for density functional theory. So phi of r is 1 over L to the 3 over 2 e to the I k dot r. And we can choose to notate that if we want to. So what we see is that the interaction energy, in this case, is the expectation value of the interaction operator in the non-interacting ground state. That's something that we will touch on repeatedly. Now, how do we evaluate this term? As before, we will have two kinds of terms, so let's write this out. So we're going to make the expectation value of the operator, psi t is given by, so the first term is an electrostatic type term, it's half times the sum over I and j. Now this time I'm including both all i's and j's because I've got the two terms which will cancel out, as we saw with Hartree-Fock. dx1, dx2, actually let me just change that, I'm going to make these dr's rather than dx's, just for simplicity, and we'll assume that we're going to sum over spin dr1, dr2 of phi I of r1 squared e squared over 4 pi epsilon naught ri, sorry not ri, that should be r1, there we go, r1 minus r2, and then we're going to have phi j of r2 squared. So that's the standard electrostatic type operator we've seen before. So in this case we've got a phi I star of r1, phi I of r1, which gives us the square modulus. And then the second term is an exchange term, it's the sum over I and j of the double integral, again dr1, dr2, and now we have phi I star of r1, phi j of r2, e squared over 4 pi epsilon naught r1 minus r2, phi I of r2, phi j star of r2. That's the exchange term where all of the complexity in quantum mechanics comes from. The first of these two terms, the electrostatic term, cancels with the other electrostatic terms that we've been considering. So we will have three contributions to the electrostatic energy. We'll have the electron-electron electrostatic energy, which we've just written down here. We will have the positive background charge interacting with itself, which will take on exactly the same form as the electron-electron density, electrostatic energy. And then cancelling both of those is the interaction between the electrons and the positive neutral background. Sorry, positive neutralizing background. So from now on, we're going to ignore that electrostatic term. So we're just coming to the point where we have to think about the exchange term, and we will want to substitute in for the plane wave solutions. If we do that, we find the following. Ex is equal to minus 1 over omega times sum over k1 and k2. That's equivalent to the sum over I and j. Double integral over dr1 dr2 of e to the I k1 minus k2 dotted with r2 minus r1. And then we have an e squared over 4 pi epsilon naught r1 minus r2. We can evaluate the integral using a simple identity, which is that the integral e to the I k dot r over r dr is equal to 4 pi over k squared. In which case we now find that the exchange energy Ex is given by minus e squared over epsilon naught omega multiplied by the sum over k1 and k2 of 1 over k1 minus k2 squared. As we've seen before, we're going to assume that we've got a very large system, so the spacing between the k vectors is small, and therefore we're going to replace this with an integral. When we do that, we're also going to consider calculating the exchange energy per electron. This is something we've been doing quite a lot, is looking at the energy per electron. So we're going to write epsilon x is equal to capital Ex divided by n, the number of electrons, and that's going to be written as follows. You've got minus e squared omega over epsilon naught 2 pi to the 6th n, and notice we've got an omega on the top now in the numerator rather than the denominator, because there's a double factor of the volume of k space, which gives you an omega squared in the numerator. Now we're going to have a double integral in both cases up to the Fermi wave vector of dk1 dk2 1 over k1 minus k2 squared. It can be shown that the integral is equivalent to 4 pi squared kf to the 4th, and so when we substitute that in, we find that the exchange energy per electron is minus e squared over epsilon naught times 2 pi to the 6th, with a rho, where we've got n over omega being rho, 4 pi squared kf to the 4th. Now if we substitute in for kf, the Fermi vector, and make a couple of other substitutions, then we find the following. We get minus e squared over 4 pi epsilon naught multiplied by 3/4 of 3 rho over pi to the 1/3. And here we've used the fact that kf is equal to 3 pi squared rho to the 1/3. Now recall that the kinetic energy per electron, epsilon kinetic, which is the same in both cases, is both interacting and non-interacting, is 3 h bar squared over 10 into 3 pi squared rho. 3 is not very clear, let me just change that. 3 pi squared rho to the 2/3. It's now quite instructive to compare these two formulae and think about how they depend on the electron density. Notice that in both cases we can write these energies in terms of the electron density. This is something that has been true for all of the uniform electron gases, that we're able to write everything in terms of the electron density, which is an important point and which leads us into the ideas behind density functional theory. But notice the powers. So in the case of the kinetic energy, it's rho to the 2/3, and in the case of the exchange energy, it's rho to the 1/3. The exchange energy is also negative, so that tends to bind systems together. But notice that as we go to larger, higher densities, the kinetic energy term is going to dominate over the exchange energy term. In other words, the many-body interactions, the interactions between the electrons, will become less important as we go to higher densities of electrons. So that finishes these brief lectures on the uniform electron gas. We're going to turn next to Thomas Fermi theory, which is a way of trying to approach the solution of the many-body problem using the electron density. It's a very crude theory, but it's a nice introduction to the ideas behind density functional theory, which is what we'll move to after that.